In previous video, we understood how to calculate location counter value. Once we have completed calculating the location counter value, we have to calculate the object. First instruction in this program is sum start 0. Start is a assembler directive, so there is no object code for start assembler directive. Next instruction is first clear X. This is format 2 instruction. So format 2 instruction format is opcode 8-bit, register 1 4-bit and register 2 4-bit. So first we have to write it opcode for clear. Unique mnemonic code which they have given for clear is B4. This will be given in the question itself. So write this B4 in 8-bit. B4, you have to write it in 8-bit. Next, we have to identify which register they have used it in the instruction, that is X. So value of X is 1. So we have to write it 1 for in the register 1 field. So 0 0 0 1. And there is no register 2 in this instruction. So that means I have to set register 2 value as 0 0. So final object code which we have obtained for first clear X is B410. Next instruction is LDA hash 0. So opcode for LDA they have given in the question, that is 0 0. So first I have to write 0 0 in 8 bits. We have to write that 0 0 in N and I bit itself. After checking the instruction, based on the addressing mode, we have to overwrite N and I bit. Here hash is used. That means it is immediate addressing mode. So change value of I bit as 1 and N bit as 0. There is no register X is used in this instruction. That means I have to set it X as 0. And it is immediate addressing mode and constant values directly specified in the instruction. So no need of relative addressing mode. So we have to set B and P value as 0 and E value for format 3 is 0. So in place of displacement, because constant value is directly mentioned in the instruction, we have to write 0 in terms of 12 bits. 0 0 0. Value of 0 we have to write it in 12. Then combine 4 bits. So first 4 indicates 0. Next it indicates 1 and it is 0 0 0 0. The object code which you have computed for this instruction is 0 1 0 0 0 0. The next instruction is of length 4. So there is plus in it. So it is format 4 instruction. So first write opcode of LDP, that is 68 in 8-bit. Then depending on the addressing mode, change N and I bit. Hash is used, so you have to set I bit as 1 and N bit as 0. And there is no register X, so I have to set X value as 0. And for format 4 instruction, always you have to set B and P value as 0 and E value as 1. This is all default value for format 4 instruction. Next, I have to write it address. So operand is total. Where total is located? Total is located at the address 178C. So this 178C, we have to write it in 4 bits value, and this includes only 16 bits. So before that I have to write it 0. So what is the address? 0 0 0 0 0 0 1, 7 is 0 1 1 1, 1 0 0 0 and C is 1 1 0 0. So value is 0178C. So then combine 4 bits, you'll get answer as 6910178C. So object code for plus LDB hash total instruction is 6910178C. Next instruction is base total. Base is assembler directive. So there is no object code for base assembler directive. Next instruction is loop add table comma, which is length is 3. So that means you have to write it format 3. And next opcode of add is 18. So write it in 8 bits and then write n and I. So there is no hash and X symbol in the instruction. So I have to set n and I bit both as 1 and 1. This indicates simple addressing, and X register is used in the instruction. So I have to set X bit as 1. And here I have to go with base and PC relative addressing mode. Either base or PC relative. By default, I have to choose PC relative addressing mode to calculate the displacement. So P value I'll set it 0 and B as E value 0 for format 3 instruction. So now to calculate displacement, so here in this operand which we have used it as table. Where table is located? Table is located at the location counter value 0013. So target address for table is 001C. And what is PC value? PC value indicates next executable instruction address. That is 0C. If we subtract, then I'll get a displacement. So this is PC value. Target address minus PC value will give me the displacement value. So what is the displacement? 01. So write it in 12. 0. So if the displacement will not fit in 12 bit, then I have to go with base relative addressing. But 010 will fit in 12 bit. So we have to use PC relative one. So now combine 4 bit and we'll get to know what is object code. So 1 and this is A 0 1 0. So 1 B A 0 1 0 is object code which is generated for this particular instruction. Instruction is SICXE count. Where count is located? It is at the target address. So first we'll write opcode. Opcode is 2C. So we have written it in 8 bit. There is no hash at instruction. So change n and I bit as 1. There is no X. So X value is 2. Initially we'll go with PC value and then base relative setting as 0. E value is 0 for format 3 instruction. So target address as we have already discussed, that is 001, and then if I subtract, I'll get it. I have to subtract with PC value. Which is a PC value? PC value is 00F. So PC is F. If I subtract 0019 and 00F, I'll get the answer as 00. So this easily fits in 12 bits. So I'll consider last 3 bits, that is 00, 00 and 1, 1, 0, 1. So final object code is 2 F 2 0 0 9. So this is the final object code for SICXE count. 2 F 2. Next instruction is JLT2. So opcode of JLT is 38. First we'll write it. And again there is no hash ended. So we have it as 1 and 1. There is no X register. So C. Initially I'll go with P. So 0 and then E value I set it as. So where loop is located, target address is 009. 0 is target. Next, what is the PC value? PC value is 0012. Now, target address is a smaller value and PC is a larger one. You will get negative placement. So negative value you will get it. So if we are getting negative value, that means in hexadecimal we are converting it to 2's complement. So 2's complement number we are going to get it as a negative number. So here you will get answer as, if we subtract in calci, you will get somewhat answer as F, F, F7. So even though here you are getting 4 digit, but we are considering only last 3 digit as a valid displacement, because so difference of these two numbers is not greater than 1000. So if it is greater than 1000, difference of any two number is, if it is greater than 1000, then we can write that, we cannot write that displacement in 12 bits. So it will, then we cannot use PC relative addressing mode, we have to go with base relative. Now the difference is lesser than 1000. So this fits in 12 bits. So I'll consider only last 3 digits, F, F and 7. So what is the final object code? Here it is 3 and 2 F, F, 7. The object code which we have obtained is 3 F, 7. If difference is more than 1000, then we have to go with base relative. But here difference is less than 1000, so we will use PC relative. Next instruction is SDA total. So opcode is 0, C. So we'll change N and I bit. X bit also will set it because there is no X register used instruction. Next, again we'll go with PC relative. So B I'll set it as 0, P I'll set it as 1, S 0. So first I'll identify what is displacement. Target address, where total is located. Total is located at the address 178. So 178 and PC value, if I take PC value is 0015. In this case, difference I am getting it as more than 1000. So if difference is more than 1000, then we can, that displacement will not fit it in 12 bits. So then we cannot go with PC relative. We have to use base relative addressing. So we'll go with base relative addressing mode. Base relative addressing. So we'll change B value as 1 and P value as 0. So now we'll calculate the display. If I use base relative, target address will be same 1, 8. But instead of taking PC value, now I am taking base value. Base value is here mentioned with help of base assembler directive, base total. That means address value of this total is stored in base register. That is address. Address is 1786. So base register also contain 178C. So if I take the difference, I'll get answer as 0. So this 0, 3 zeros will fit it in displacement of 12 bits. So that means 0. So displacement is 0. So what is the final object code then? So F 0, 1, 0, that is 4, 0. Object code for that instruction is 0F4040. Next instruction is STCH buffer, X. So value of opcode is 54. So already we have written. There is no hash and to change n and I bit as 1 and 1. X is present, so you have to write it X value as well. Initially I will go with PC relative, so 0, PXX as 1. E anyways. So now we'll calculate target address. So target address is buffer. Buffer is located at 178F. 78F. And then PC value is instruction address, that is 201. So if I subtract to calculate the displacement, now I am getting difference as more than 1000. So if difference is more than 1000, anyways this bits will not fit it in 12-bit displacement field. So we have to change the relative addressing mode. So we have to go with PC relative. Sorry, PC relative is not possible. So we have to go with base relative address. Base relative address. So B value is set it as 1 and P value is set it as 0. So now displacement will calculate it. Target address will not change, that is 178F, and base value is 178C. So if I take the difference, I'll get it value as 003. So 0, 0, 0, 0, 2, 0, 1. So this fits 12 bit. So I have to, what is the final object code? Final object code is 5, 7, 2, 1, 1 is 7, 0, 1, 7. And next we have 1, 1, 0, 0. This is 8 plus 4, 12. That indicates next 0, 3. So final code is 573 0, 3. 576. Next byte x09. So if what is the object code of byte x09? So that means here we are just generating hexadecimal constant. So what is the value? Already hexadecimal value they have given. So same thing you have to write it in 1 by 2. And next instruction is reserve word 1. There is no object code for reserve word and reserve byte. So no object code for reserve word and reserve byte. And end. So this is what the final object code we have obtained for this particular program. So once we have written object code, then we have to write it object program. The simplest object program contains 3 types of record: header record, text record and end record. So if any format for instruction and there is a necessity of program relocation, then we'll go with modification record. Always better to write modification record. So first we'll write header record. Header record format is in column 1 I have to mention H, column 2 to 7 program name, column 8 to 13 starting address of the object program and column 14 to 19 length of the object program in bytes. So first I'll write it H, then we have to identify start program name, that is sum. So sum we have to write it. Only 3 letters are there. So next 3 we have to leave it blank. Next I have to write it starting address of the object program. Here they have given it as 0. So I have to fill it all 0. So now if they given starting address as 1000, then only last 4 digit you have to write it 1000 and it is preceded by 20. Next, we have to calculate length of the object program in byte. How to calculate the length? So I have to first identify what is last address. That is 278F. And what is the starting address? That is 000. So along with end, we have last address as 278F and starting address as 000. Subtract these two values. So 278F is 000. I'll get it answer as 278F. This is length of the program. So length of the program, we write it as 00278F. After writing header record, then we have to write a text record. So this is the format of text record. So column 1, I write it T. Next, I have to write it starting address for object code in this record. So we have just started writing the text record. No other text record we have written previously. So first I'll write it 000. So 00 as starting it. Next, length of the record, object code in this record, I'll keep it blank. Next, column 10 to 16, we have to start filling the value. So column 10 to 16, that means we have to start writing all the object code. So column 10 to 69, that means the total 60 digit you can write it. 60 columns you can fill it. So 2 columns for 1 byte. That indicates 60 by 2. That means total 30 byte you can write. So now if you reach 30 byte, then you have to stop it and then you have to start writing next text record. So you cannot write it more than 30 byte in one text record. So first B410 I have written. So length is not 30 bytes. So then I can continue in the same text record. So next object code is 01000. So that we have to write it. The same way I'll just write, I have written all object codes. So now I'll just check the length. 3410 is length is 2 and 0100's length is 3. This is 4, 3, 3, 3, 3, 3 and 1. If I counted all these value, length value, 2 plus 3, 5, 5 plus 4, 9, 9 plus 3, 12, 12 plus 3, 15, 18, next 21, 24 and then 25. So total we have used it only 25 bytes. So not 30 bytes. So that means all these object code will fit it in single text record. So length of the object code we have obtained is what? 25 bytes in decimal value. So then the equivalent value of this 25 byte in hexadecimal is 19. So we have to, in text record, we have to write it hexadecimal value as a length. So that means we have to write it 19 as length of the object code in this text record. So 19. After writing text record, we have to check, is there any format 4 instruction in our program? If so, we have to write a modification record. So modification record format is yum, and then we have to write it starting location of the address field to be modified. So starting location I have to identify. So this instruction starts from 005. So we have stored this value from 005. So if I take this entire object code at 005 location, we have stored 69, then 6th location 10, 7th location 17, and 8th location we have stored 8C. So now in this entire format 4 instruction, 0178C represents address. If I write it in format 4, last 20 bit mentions address. So now we have to change this address. So we cannot change it 6.5 here. So what we are writing? We are writing from 006 only we have to change the value. So starting location of the address field to be modified 0006. Next, I have to identify length of the address field to be modified because entire all 3 bytes we are not modifying it. We are modifying only half of bytes. So how many half byte you have to modify? Only address field you have to modify. 1, 2, 3, 4 and 5. So length of the address field to be modified in half byte is 0, 5. After writing modification record, then we can write it end record. So column 1 indicates E, and then I have to write it address of first executable instruction. Address of first executable instruction is 0. So I have to write it address as 0 in next 6 columns. So we have written final object program with header record, text record, modification record, and end record. So this is final object program. I hope you understood all the concept. Thank you. Happy learning.